All right, welcome, Comp Stats folks. Today we're going to cover non-structural bootstrap methods for time series data. Now, as a way of background, we did cover the bootstrap. We covered it for independent data. And dependent data, like time series data, requires some special techniques. And so we're going to kind of work over a broad brush of techniques that we can use to better analyze our time series data. So let's talk about motivation. One easy way to motivate this is, well, what would happen if we didn't do this at all? So we're going to call that a naive application, and that's going to incorrectly assume that we actually could use these same techniques we use for independent data. And mentally, you can kind of imagine as we're creating these pseudo data sets, we are going to be ditching the underlying covariance structure that was present in the data. Obviously, when we were sampling with replacement from that original data, there's no way that we could possibly preserve that covariance structure in that process. So depending on the data that we have and our statistic of interest, this is going to result in something, right? Because we're missing out on that covariance structure. It's not clear whether it's going to result in larger or narrower confidence intervals, for example, but and we'll talk about why, but it's clear that it will have an impact because we just lost that covariance structure. And anything that depended on it won't have that incorporated. So we won't be able to simply use more pseudo data sets and even with more data sets, there's no guarantee of consistency of our estimation here, or even with larger original samples. Mathematically, we can frame this for time series with these couple of equations here. Again, we're talking about, here we're going to focus, in most of the presentation, we're going to focus on the sample mean as being our feature of interest and looking at the variance of that estimator. And here we can see that as we express that, we're going to have the covariance embedded in that definition. We're not relying on independent data, right? So that's going to be an important part that contributes to that equation. For time series data, you can see this equation. It's also in the text is 9.24. There's a few versions of this. Basically, for a time series, you can rewrite that equation pretty easily using autocorrelation lag and kind of this lead term of the variance of x1. And so as the text cites, as n goes to infinity, as our sample size goes to infinity, this variance in the bootstrap of the x star bar minus x bar is going to head to this variance of this x1 term. These covariance terms are not going to be reflected where they are reflected, in smaller n. So if we do nothing, we know that we don't have this consistent definition. We're going to lose out on this covariance terms in our formulation. So what do we do? Well, we've got two families of approaches. One family is this structural family that's reliant on a model for the data generation. You can kind of think of it like, you've been exposed to some linear models, some ARIMA style models where you are, parameterizing the model, the data generation process. And here we're looking at the dependent structure of the error terms, the disturbances in that model. So we're taking advantage of the fact that we can model it and using the resulting model of the error terms to get a more refined view on this. And this can get more and more complicated with more and more variance. You'll see the word sieve used a lot in the texts. And that's really using a sequence of these models for approximation. So it can get more complicated, more robust. In these cases, it's at least partially using a model for part of this process. We're focused today on non-structural methods, so they're non-reliant on given model structure, and that opens them up to maybe a little less power in terms of their approach, but more avenues where we can apply them. So applications to nonlinear time series, to spatial data, and the key feature that we're going to talk about is the introduction of blocks as a mechanism to get at this problem without relying on a model structure. So that's where we're going to focus today. So a quick refresher on stationary distributions. We're going to talk about this briefly because we're going to need it in our development. Stationary distributions, as we recall, are they have a distribution of a sequence of random variables that are shift invariant in time. And so that's probably better expressed by this equation. So the sequence of these random variables that we see, their distribution is stationary if it doesn't matter what time we look at it from. And we covered this with Markov chains. So some comments here. There are other definitions of stationarity, particularly for spatial data. There's weak stationarity, which doesn't involve quite the same full structure here. It's more about the first cross moment. We're not going to cover that here. We will need, though, for our original sample to come from a stationary distribution for our blocking strategy to work. So we're going to make that assumption going forward. Not all of our approaches will result in a pseudo data set that is stationary. We are requiring it to even start, but we're going to see that that's a kind of distinguishing feature of some of our approaches. Great. So now let's get in to the actual meat of blocking. So blocking is this fundamental technique. What does it mean? So we're going to say here that when we block the data, we're going to create groups of data where the covariance structure is preserved. So you can imagine kind of snipping the data, and it might have two edges, but you're going to preserve the sequence of data within that block. So you're preserving the covariance structure. So some attention must go into how we create the blocks and the consequences of introducing the blocks. But once you've done all that upfront work, the evaluation of your feature of interest, your statistical function, your x bar star in our case, and all of its properties, that's all just as straightforward as it was when we had independent data. So you got to do some heavy lifting in order to get your data in place and allow yourself the pseudo data sets, but that's the heavy lifting. So we've got lots of different techniques. We're going to cover 3 here in depth and code, and we're going to start with the easiest, obviously. So we're going to start with non-moving blocks. So non-moving blocks are strict partitions of the data. So we're going to assume there's n data items in our original sample. We're going to partition them into blocks of size L. We'll end up with B blocks, but you can imagine the first block is just items 1 through L 1 through L minus 1, sorry, of that original sample. So it's a strict partition of the data, and pretty simplistic. Once we build those blocks, then we're going to independently sample those with replacement. So that's the thing we're sampling in not the original data. Now we're sampling in terms of blocks. And then once we have the blocks, we can stitch them together. So we're preserving structure within the block. Obviously, we're introducing some discontinuity potentially between, or some new effects between blocks, and we can see any one block more than once because we're sampling with replacement. So pretty straightforward extension, just in terms of looking at blocks. So some comments: we're retaining the order and structure within the blocks. That's the whole point. The order in which the blocks are reassembled doesn't matter because we're assuming stationary time series to start for the original data set that they're drawn from. Generally, this is not the best approach to blocking. Kind of intuitive why, like the data generation process probably didn't have strict partitions. So this is kind of a straw man, generally not the best. So let's talk about something better, which is moving blocks. Moving blocks, we replace those strict partitions with overlapping blocks. Again, still a fixed length L. So our block definition changes, and then we have many more blocks because we have that block that started from item 1 that went to L minus 1. Then we have a block starting at item 2, another one starting at item 3. They're all the same fixed length, but we have many more blocks to choose from. And we'll get some of this overlapping nature in our data. So again, we're using the blocks. We're going to sample them with replacement, et cetera, et cetera. And some comments. We generally expect moving blocks to have superior performance over non-moving blocks. That's dependent on the statistic of interest and the data set, so kind of with a little grain of salt. But the text cites an AMSE asymptotic mean squared error improvement of about 31% by using moving blocks for a broader set of data. So moving blocks are good, we think. They present some additional issues related to the very edges of that original sample that we will address later. Here's an illustration quickly on how moving blocks look like. You can see kind of a range of potential candidate blocks. They're overlapping, of course, because that's what we're doing in the moving blocks. We resample them and stitch them together so that we get a pseudo data set. So that's kind of the visual intuition. I'm not going to cover the code. You can see the code yourself, but this part of the code is actually pretty easy because all you're doing is creating blocks, sampling from them, and reconstituting your pseudo data set. This stuff is actually pretty easy. We'll talk about what's not later. So here we're going to do a comparison, and this is actually the same exact comparison so that you can follow along in the text if you choose. We're using the GDP change data in example 9.9 with a fixed block length of 8. Here this is the non-moving block bootstrap, this one's the moving, and this is an implementation of the naive approach that we started with. So here we chose a block length of 1, and so we're not preserving anything. There's no covariance structure within these blocks to preserve because we're taking an item of 1. So this is a way of mimicking a naive approach that, and using the same functions, honestly. And you can see the standard deviation of our estimator is different here when we use the naive approach. Now, in this particular case, it happens to be that these are less in the non-moving and moving case. Now, they're less if we go back to look at this GDP change data because a lot of the covariance terms are negative. So it's not guaranteed that it's going to be less by using moving block bootstrap. What is guaranteed is that it's going to incorporate the covariance structure that's in the data, which is exactly what we want. There are some extensions to this. Once we consider blocks, we like blocks. It helps us maintain covariance structure, but then we are worried about what flaws emerge, and particularly what happens when we stitch these two blocks together and create data that wasn't contiguous before. So one idea is to taper those blocks and downweight the ends. Another is to do matching, to attempt to stitch the blocks together that were nearby in the original data. This is kind of like, if you think about wood, blocks of wood, hardwood floors, you're trying to match those blocks together. I think in the research that I've done, these seem pretty rarely used, but might be right for your data set. So now we're going to talk about edge effects. And this is there's kind of two broad ways to deal with edge effects. So here we're not talking about the edges between blocks, but the edges at the very edge of our original data sample. So we might intuitively prefer moving blocks. We seem like we actually have a pretty strong preference, at least on this side of the desk. But they do have edge effects, and you can kind of see why. This, in our original sample, x1 and xn just don't have many blocks that they will appear in, so they're not going to get sampled at the same frequency. And so what we get in our bootstrap estimator, our feature of interest is a model by theta. Theta star hat is going to be a biased estimator from that if we use moving blocks. Non-moving blocks, in contrast, well, we threw it a lot of shade before. We didn't really like non-moving blocks. But it is true that the data is equally represented, so the bootstrap estimator theta star hat in the non-moving block is unbiased. So, we're going to chart bravely forward and try to deal with the fact that we want to use moving blocks, even though it's got a biased estimator. So one approach, and I'm going to cover this briefly so that we can fit the presentation in the 20 minutes, but one approach that we can take is pivoting. We saw pivoting before in independent data. Our goal there was to use a transformational pivot to come up with an unbiased estimator after transformation with a variance that didn't depend on that theta parameter, that theta feature of interest. We used a really straightforward student transform before. We can't quite do that here in dependent data for two reasons. The centering is harder and the variance estimator is also harder. So for centering the data, a real challenge here is coming up with this expectation of theta star hat in the bootstrap distribution. So that's not always tractable, and it really depends on how hairy our feature of interest, our T, T of F hat is, to be able to achieve that. So a lot of our discussion from here going forward, based on the assumption that we could formulate as a function of the sample mean, so it's a smooth function model. The variance is actually even hairier. We've got this variance that we would use naively that we wouldn't think about a whole lot, but it's covered a lot in the Lahiri text. But this has much more severe consequences if we try to use this naively. And there's a couple of ready approximations here. We're using an approximation that's listed in the text, 9.27, that uses X bar from the original data. So this is all in terms of the original data. There's another formulation that uses it in our bootstrapped data, pseudo data sets, which is basically equivalent. But the key is we have to think more about the pivot than we did when we did independent data. I'm going to leave that quickly to talk about a different family of approaches, which is how can we create a blocking design that doesn't have edge effects at all, and maybe we can bypass some of these problems. And one pretty cool, clever way, I think, that builds on what we talked about before is the stationary block bootstrap. This is presented by Politis and Romano. Politis's writing is very clear with very short papers. I encourage you, if you're interested in this stuff, to go to the source over the text. And here we're introducing a variable length block. So before we had fixed length blocks, now we're introducing variable length. We're also introducing a wrapping design. And that means if we start a block at the very end of our observations at like item n, right at the very end, we're going to just keep going to item 1, item 2, item 3. So we're just going to wrap around. So we'll never hit an edge. So edge effects are explicitly accounted for. Great. The resulting pseudo data sets are stationary, conditional on the original data set, which is great. Very useful for time series. It's not true of the moving or non-moving block design. So that's obviously it's in the name. It's a key attractant to using this method. We have a challenge of choosing this probability p. So the length is determined by geometric distribution. So you have p between 0 and 1. You have to choose it. It's kind of like choosing the fixed block length. Politis argues that it's less crucial, that this is kind of a weighted average of what we would have gotten with fixed block lengths. But to my mind, you still have to choose it. So I'm not sure that that's exactly a huge win. And he mentions, or they mention, data-oriented choices are desirable. I don't see anyone really using data-oriented choices. It's much more common that kind of back into the probability by looking at expected block length and kind of save that problem. So great, we skipped all over the key issue, which is where do we get the block length L? So now we're gonna have to face up to that. So block size. So how are we gonna figure out the block size? So here, let's start with the motivation, which is that block length is important. This is the same GDP data that we had before, where we said the standard area when we took the naive was really high, that 0.33. When it shows a block length of 8, it was much lower. This curve doesn't say which one to choose. It's just saying that you choose a different block length, you're going to get a different standard error estimate for your feature of interest. So that's just to say it matters, but it's hard to choose. We have some basic intuition, though. Let's cover that. Politis and others point out you can kind of consider this a smoothing parameter. Great. But if we choose too small, we're going to effectively lose the covariance structure that we're trying to keep. Well, that's a shame. That's what we just showed in the naive example. This is effectively, one way to word this is that we're increasing the bias of the bootstrap method in this way. And what's the reverse? Well, if we choose too large a block size, we're not introducing enough variation of pseudo data sets. We're reflecting our original sample too closely. Sounds a lot like overfitting, and here we have relatively high variance. So that's a framing of this. So we're looking for something that's not those extremes. And the optimal is going to depend a lot on multiple factors, so it's hard. We're going to need to look at the data generated process, the statistic of interest, and the purpose for which is being used, which is important. This bias variance distribution estimation affects the math that we're about to see in the next page. So here's our broad goal. We're trying to use Bootstrap to help us understand the properties of the statistic, of course. But the Bootstrap estimators have their own properties. So they have their own bias, variance, and mean squared error. So this is kind of the next level of looking at this Bootstrap estimator. So one way to think about this is let's try to minimize the mean squared error of either the bias or variance of that Bootstrap estimator. So that would allow us to, and you can think about that as a function of this block length. So that's something we can minimize and go after. And we're going to show a subsequencing variant. There's another one that Lahiri presents that's also in our text. And there's a plugin method that Politis and White recommend. But this one, subsequencing, I believe it's hard enough. So let's go into that. So here we're looking, and we've got to focus. We're looking at this bias of our estimator and what its properties are here. And so we're eventually getting down to what is the mean squared error of that that bootstrap estimator. And here we can see for the bias and variance, if we chose the bias, that is on the order of the cube root of n. That's important to the definition that we're going to look at. It's not always true. That's true because we chose this bias or variance of the estimator. So the subsampling approach is pretty clever. We're creating subsequences. So we create a subsequence and we use the block bootstrap with a potential candidate block length that we think it might be. And that allows us, because we're using multiple subsequences and we're using the block bootstrap on them, we can get at a point estimate of that phi that we saw on the page before. That allows us to calculate an estimator for that mean squared error, because otherwise we wouldn't be able to. And we can look at multiple candidate lengths and choose an optimal value. That's considering this subsequence length m, so we have to, at the end, rescale our estimate. And this, again, the key here is that we're looking at something that's on this third root of n power for this optimal length, which can also just help us just kind of as a heuristic. So here I showed this example in the deck that's the optimal length for that GDP data. It's actually pretty short. It's 2 based on this using the bias of the estimator formulation and this subsequence method. 8, if you think about it, is pretty large for a data set of 40 for that block length. But so we're looking at a shorter optimal block length from our kind of coded here. So some endnotes. So we looked at motivation for different approaches. We looked at blocking. There's a lot of different kinds of blocking methods, and we looked at complications from edge effects, and particularly how to select a block size, which is the most challenging piece. Here's some references. I recommend the Davison and Hinckley text, or this draft text by Shalizi. If you're looking for more information, they're kind of at the right level and pretty informative. And then again, I recommend a lot of the papers by Demetrius. This Hall and Horowitz paper is the subsequencing paper. And I invite you to look at the code, and thank you for your time.